fractions. So what is the mole fraction? What is that? It's basically saying percentage of the moles in a mixture, but in decimal form. That's what the mole fraction is. So if you have a problem that asks you, oh, give me the mole fraction of this, what would the mole fraction be for not oxygen? Right? It would be whatever this value came out to be. So mole fraction of oxygen from this part would be 0.42. Okay. So it's a unitless number because the moles cancel. It's just a percentage. Let me ask you this question. What is the percentage of the oxygen gas in this mixture? It's really easy. It's right in front of you. What is this as a percentage? 42%. Right. And this would be whatever this divided by 2.1 would come out to be, which really would be like 58%, right? So the mole fraction of helium is 0.58. So you can think of the mole fraction as a percentage of the gas, but in decimal form. Okay. All right. Okay. Any questions on mole fraction, partial pressure? Okay. So we were talking about real gases. And we really should talk a little bit about kinetic molecular theory and what the postulates are from that. Because ideal gas laws are derived and assumed from the kinetic molecular theory. So the postulates of kinetic molecular theory include, and I've got the main ones highlighted in red, they're probably the most important ones. But you're assuming the gas particles are always moving in constant motion. Here's the big one though. Kinetic molecular theory assumes that the attraction between gas particles is negligible. In other words, the collisions between gas particles, they just bounce off and they're completely elastic. Okay, which kind of goes along with the third postulate. So the reason why gases are gases is because when they collide, they don't stick together and start coalescing into a liquid or a solid. Right? They just bounce off. So this is assuming no attraction between particles. That's how we get ideal behavior, right? No attractions between gas particles. It is assuming ideal behavior. So when you say a gas behaves like an ideal gas, what you're saying is that it obeys kinetic molecular theory. Okay, that's what you're saying. Another postulate that's a big one: gas particles take up negligible volume. In other words, we have lots and lots of gas particles in this room, but they take a negligible volume, so we're just walking through the room. We don't actually have to run into gas particles, but we actually are because we have nitrogen and oxygen molecules, a plethora of them in the room here. They're hitting us in the face as we're sitting here, as I'm up here speaking. But we're assuming that we have ideal behavior. That volume taken up by the gas particles themselves are negligible. Right? The atoms have no volume. That's what we're saying. We know that that's false, but we're assuming that to be the case here for ideal behavior. Another one that's interesting is gas particles have the same average kinetic energy at a given temperature. This one is a little bit esoteric, but I have a real-world example that I used in my research that uses this concept for an instrument, a scientific apparatus. So I'll share that with you. Here's a diagram that illustrates that last postulate of the kinetic molecular theory. All gases have the same average kinetic energy at a given temperature. What this graph is showing is that you have a relative number of molecules with a given velocity. So this basically is the number of gas particles, and then here's the velocity of that particle. Okay, so as a molecule moves faster, it tends to have a lighter mass. So this is the kinetic energy equation, 1/2 times mass times velocity squared. So as this velocity squared, or as this velocity gets faster, okay, it's going to also have a higher kinetic energy. Okay, the heavier molecules, they move more slowly, so these are the heavier ones. If you look at these gases, what do you notice about them? oxygen 32 grams per mole, nitrogen 28 grams per mole, water 18 grams per mole, helium 4 grams per mole, hydrogen 2 grams per mole. Okay, those are the molar masses of those gases. So as you see, the heavier gas particles travel at a lower velocity. Okay, they move more slowly. The lighter gases, on average, move at a higher velocity. So it's basically comparing Hulk versus the Flash. Hulk is fast, but Flash is the fastest. Okay, he's smaller, he's lighter. Hulk, he's got more mass to him. But let me ask you this question: would you rather be run over by the Hulk, or would you rather be run over by Flash? And the answer is, you'd rather just not be run over by either one of them, because it's going to hurt just as bad. Flash is going to hit you faster, but Hulk is going to hit you with more mass. So can you see how Hulk and Flash could have the same average kinetic energy at a given temperature? Okay, you're still being hit with the same amount of kinetic energy, which is the energy of motion, right? And that's what the kinetic molecular theory is telling you, okay, in this diagram. Okay, heavier molecules move slowly, more slowly. Lighter molecules move more quickly on average, okay? But all of these gases at a given temperature, which is not in this graph, have the same average kinetic energy, okay? Okay, so what this diagram in particular is showing you, heavier gas molecules move more slowly, lighter gas molecules move at a faster speed. But if I gave you a question, which one of these gases has the greatest kinetic energy? The answer would be none of them have the greatest, none of them have the lowest, they all have the same kinetic energy. Okay. Looking at gas velocity versus temperature though, like what happens, so notice how hydrogen has sort of a distribution of velocities, okay, but what we don't know is what does this distribution look like at a given temperature, all right, how does temperature affect that velocity? So gas molecules will travel at different speeds at different temperatures. If you heat up a gas, the gas particles move at a faster speed, okay, which is why pressure increases when you heat up a gas, right? The gas expands because the gas particles are moving more quickly.
Like when water boils?
Yeah, when water boils, the water molecules, even in the liquid, are moving more quickly to the point where they're starting to escape into the gas phase. Okay, this distribution of speeds at a given temperature, we call that statistical pattern the Boltzmann distribution. Okay, and from the Boltzmann distribution, the root mean square velocity can be derived. All right, so this equation here is new, you haven't seen it yet. So the root mean square velocity, RMS, that's what that means, root mean squared, is the square root of 3 times RT over the molar mass of the gas. R in this case is the gas constant, but it's in different units. It's in units of joules per mole Kelvin instead of liters atmospheres per mole Kelvin. Okay, so it's just the gas constant but with different units. Another useful conversion is 1 joule is equal to a kilogram meter squared per second squared. So this is sort of like how kinetic energy of motion, mass times velocity squared, is related to energy in joules. Okay, so that's just a nice useful conversion. So speaking of a gas velocity distribution at a given temperature. So here's a graph showing how nitrogen varies in speed at given temperatures. So this is not different gases now, this is different temperatures for a single gas. So if we just took nitrogen from that past graph, and then we looked at the velocity distributions at different temperatures, this is what we'd be looking at. So, so clearly at lower temperatures, what do you notice about the velocity? It's slower, right? You cool down the gas molecules move more slowly. 1,000 Kelvin, all right, much hotter. Now the Boltzmann distribution of velocities has shifted, okay? And then at 2,000 Kelvin, even hotter, now the average velocity is even more distributed. What you'll also notice though is that the distribution of speeds gets wider as you raise the temperature, right? So now I used to look at gas molecules inside a vacuum, which is really, really cold, okay? And the velocities tend to get really narrow, okay, in a vacuum because things are so cold. But that's nice when you're trying to do light detection and spectroscopy, which is what I was trying to do. Okay. So this is different from the previous graph. You're looking at a distribution for just one gas at different temperatures in this graph. But in the other one, you were looking at a set of different gases all at the same temperature. So imagine if I wanted to look at oxygen, nitrogen, water, helium, and hydrogen. That other graph was looking maybe only at 273 Kelvin, okay? And then those different distributions of gases were only 273. So you see what the difference is? All right, so if I at least go back real quick. So imagine if you just took this, if this graph was fabricated at 273 Kelvin, this is how the different velocities of different gases compare, right? Versus just looking at nitrogen now, this is a temperature dependence of the velocities for nitrogen. And that's the difference. Okay. What do you think if I was looking at oxygen? What do you think the velocity distribution would look like for oxygen in this graph? It probably would be even more narrow, and it would be even more slower, you know, because oxygen is heavier. But it would be more slow and maybe a little higher. Right? That's what it would look like. Okay. So let's actually we'll continue this next time. All right, let's just continue this next time. We'll do sample power, root mean square.